Hello and welcome in, everybody. Happy Tuesday. My name is Brian, and we're here to do a little bit of mathematics today. Might be a little quiz, might be some ads rolling in for some of you because I had a little bit of a late start here getting set up. Yeah, so welcome on in. Let me know how your weekend went. Mine was pretty good. It was a pretty good weekend. I got my taxes done, which feels good to get all that done today. And we met some friends. We met some friends yesterday. Had some drinks yesterday. Introduced the dogs. It was a good time. Yeah, that's a nice one. 5 plus 6 times 10. Oh man, that one's totally doable mentally. But today's a big day. Today is a big day because I got my marking assignment for the Euclid mathematics contest. Yes, I do help mark the contest virtually. And I got my marking assignment over the weekend. So this is the new Euclid contest. This is the one that went out this year, the 2023. It was done on the 4th and 5th of April. And when we collect all of the papers, I have been assigned to mark questions 7 and 8 on the Euclid contest. So we're going to... Levi and I did a little bit of groundwork on a couple of these, but I want to come back, really have a go at these 4 questions specifically today, so I know exactly what they look like, and I know how to do the marking when I look at the marking key next week. Oh, Matt Loims! Hello, my friend. No, yeah, taxes. Yeah, taxes are coming in. Yeah, coming in hot. Got to get on those, yeah. It's not as bad if the government's going to give you something back, they don't really care. You can submit it as late as you want. But I wanted to do my taxes because I needed to make sure I didn't owe the government anything. That's when they start to harass you a little bit. What's going on here? Have I finally lost battery power? 5% of the battery is remaining. Well, that's not good. Do I have a backup battery? I feel like that's something I should have. I think this is the battery that I need. What a time to lose your battery, though. Holy smokes. What do I need? I need a quadruple A. Which, I cross my fingers. Let's hope that this works. Otherwise, we're in for a pretty short stream today. As I bust out of the house to go find more batteries. Uh-oh. Uh-oh. Does it go this way? Did the CRA strike? I don't know. I got an email, but I don't know if they've actually went on strike. I know that they were ready to go on strike. I mean, that would help us all out right now, wouldn't it? They just go on strike, and then that way we don't have to do taxes this year. I'll catch up with you next year. So this is 2023 question 7A. 7A. But yeah, take a look at that. Let me know if they did go on strike or not. I mean, I still submitted everything today, whether or not they went on strike. All right, what do we got going here for question 7A? A bag contains 3 red... Okay, let's draw the bag. Okay, so we got a bag, and we have a fellow removing 1 marble at a time until the bag is empty. Each marble they remove is chosen randomly from what's left over, given that the first marble is red, and the third marble is blue. What's the probability that at least 2 marble... the last 2 marbles are both blue. So we have to... basically line up all of these marbles, I guess, right? we know that the first one is going to be red, so we're going to force that choice here. And we know the third one's blue. Is that how that works? The first marble is red and the third marble is blue. Yeah, that seems right. So they announced yesterday that they're going to strike today if no agreement was reached. Oh, okay. 9 p.m. Eastern Standard Time. So that's Ontario time? So 9 p.m. Ontario time? We got a couple hours left. That's what? That's 6 o'clock my time. I got 5 hours to party. Oh, yeah, you're right. Yeah, I have it backwards, don't I? Yeah, we can't party until after we know they're on strike. And then it doesn't matter. Then we don't have to do our taxes. The 5-hour countdown. But how much tax evasion can we make in 5 hours? So this is a probability thing. So the probability is going to be, we got to find the total number of ways to draw stuff. And here we need those final two to be blue. So how many things? We have 1, 2, 3, 4, 5, 6, 7 things that we need to Is this as simple? It's not as simple as 7 factorial, but it should be 7 factorial, and we have to divide out all the duplicates, right? So the total number of ways is going to be 7 factorial. How many blues? We have 6 blue marbles, so we have to divide out those duplicates, and we have 3 red marbles, so we have to divide those out as well. So that should be our total amount. And then what we need to do is we need to get the numerator, which is going to be all of the possibilities containing 2 B's at the back end. That's going to leave us with 1, 2, 3, 4, 5 things to arrange. Does that seem reasonable? I feel like this is really similar to a problem we've done already, isn't it? But I think it's a little bit easier. And if I simplified this, I'd have 5 factorial over 7 factorial, which is a permitted fraction for probability. That makes sense. And I guess if we get rid of this 5 factorial, this would be like a 6 and a 7. This is going to be 1 over 42. 1 over 42. Does that seem reasonable? Does it seem reasonable that we have a 1 in 42 chance that the last 2 balls are blue, knowing some information about the first and the third? Yeah, 1 over 6 times 7. Yeah, that's what I'm thinking. That's what I'm thinking. And it's a light bulb question, so it shouldn't be like too crazy to solve. I don't think we have to do anything super crazy other than just assign the rest of what we have left over. So I think this will work for 7A. Let's take a look. I do have the solution keys. So let's see what they say for 7. 6 looks crazy. It looks like we're designing an American flag or something in part 6. That's kind of cool. Oh, that is a lot of work for number 6. What? All of that is number 6. Holy shit. So each possible order corresponds to a sequence of 9 colors, 3 of which are red, 6 are blue. Yep. Since we are told that the first marble is red, the third is blue, we would like to consider these sequences. Sure, the 7 blanks must be filled with the remaining stuff. Okay, so 7 choose 2. There's 21 ways of doing this because 2 of the 7 blanks must be chosen in which to place the R's. Of the 21 ways, some of them have the last 2. Okay. 10 over 21. Does the first space, the one in between the R and the B, or the first space is in the R? So it says the 7 blanks must be filled with the remaining. So they say that there's actually only 21 different. If I'm reading this correctly, they're saying there's only 21 ways to arrange these 7. Oh, yeah. How many do I have? I must have too much in the denominator. So what is 7 factorial over? And why doesn't that work? That's my question first. So if we have this situation here, understanding the common mistakes is going to be really helpful. Is this 1/6? So this is 7 times 6 factorial. Oh, this comes out to be... This comes out to be weird. So yeah, I can tell right away that I fucked something up here. Because this would be 7 over 3 times 2, which is 7/6. And the number of ways to do something can't come out to be a fraction. So I definitely fucked up somewhere in there. So what was my thought? My original thought was 1, 2, 3, 4, 5, 6. There are 7 things to arrange. But maybe what I do is I don't include these 2 things. So instead of dividing by 6 factorial and 3 factorial, I actually have to divide by 5 factorial, which is the number of blues that I'm assigning, and divide by 2 factorial, which is actually the number of red marbles. Would that make a difference? That might actually work. So if that's the case, we would have 7 times 6 times 5 factorial. Then you have 5 factorial, and this is basically a 2, right? Yeah, 42 over 2, 21. Okay, so this is what we need for the denominator. Because these cancel, right? And we get 7 times 3, 21. Yeah, okay, sweet. So that was my error. I divided by these numbers when I actually needed to subtract 1 from these numbers because I've already assigned these 2 balls. Bummer. Okay, that makes sense. And then I think we just try to do the same thing. Like if we assign these ones here, we know that we have 5 left over that we have to arrange. We have 2 of them which are red, and 3 of them, which are blue, because we have 6 blues altogether. So what does this give us if we were to expand this out? So this would be 5 times 4 times 3 factorial over 2 times 3 factorial. So this is 5 times 2, which is 10, which is what I think they have as their numerator. Okay. So I had the right idea, I just used the wrong numbers. So the probability is equal to 5 over 2 factorial, 3 factorial, and then the denominator is going to be this one. Cool. Yeah, the RB thing is what kind of what messed me up at the start there too, because I thought that I had to include them in the divisions inside my denominator. Yeah, totally. I totally get that. Okay, so I'm happy with that. That makes sense. Okay, I remember 7b being quite an interesting question. And it's usually around question 6 and 7 on this Euclid test where things start to get a bit wild. So this is the Euclid 2023 7b. So this one's asking us, determine the number of quadruples of positive integers a, b, c, d. A, B, C, and D have to be in ascending order that satisfy both systems, or both system of equations here. Around 6 and 7 is where I start in a Euclid test. Yeah, some of the initial questions are pretty boring. It's usually, yeah, usually when you start to get into like question 6 is where things start to get a little bit more interesting. So I remember when Levi and I were working on this the other day, on Sunday, we took the first equation, I think. So we can factor out A and have C plus D, and then we can factor out B and also have C plus D. So that means that A plus B and C plus D have to be factors of 2023. Right, so what we did is we took 2023, we tried to prime factor it, and it was a nasty number. 2023. It had like all 7s and like 117s in it or something silly like that. It was not a very nice number. So it's 7 times 289, and 289, I'm pretty sure it wasn't a 117. Okay, what was the... It's divisible by something weird. Oh, it's divisible by, that's 17 squared. So 2023 is 7 times 17 times 17. So let's see if we can find all of our factors. Okay, obviously 1. Not divisible by 2. Our next smallest factor is 7, then 17. Then we need 7 times 17, which is 119. We need 17 times 17, which is 289. And then we need everything. How does this work? This is a squared. This is a power of 1, so there should be 3 times 2. There should be 6 factors altogether. So I think I have all of them. Do any of these factor pairs add up to 296? And we do have to keep in mind that these factor pairs are kind of, let's see, how do we put this? They're paired together, right? They have to multiply to give me 2023. So I'm assuming that we have to kind of match them up like this. So I think I found, I think it's the green pair we want, right? And that was, I didn't plan that, but yeah, underlined in green looks like the one that we need. 7 times 289 will give us 2023. And then if we add these two up, so 7 plus 289, is that equal to 296? I think so. Yep. Okay, so now that we have that information, we now probably just need to go back and answer the statement of the question. So what do we know? We know that A plus B is probably going to be the 7, and C plus D is probably going to be the 289, but I should be careful about this. Yeah, I think A and B have to be smaller than C and D, right? So can we do that without loss of generality? And I guess it becomes a counting game now, right? So how many A's and B's can I find so that A is less than B? So I guess maybe we'll just start listing out some of the pairs. So we could take 1 and 6, we could take 2 and 5, we could take 3 and 4, and then as soon as we swap the order here, B would now become too small, right? Like if I tried to do 4 and 3, I can't take that one because A has to be less than B. But I think all the other ones were, oh, and 0, do they have to be positive integers? So 0 is not allowed. So I think there's only 3 pairs here for A and B. Now that is going to put a little bit of a restriction on our C plus D, right? So we can't, for example, take 1 and 288 because then C wouldn't be bigger than B. So if I take 1 and 6, that means C has to be at least 7. And then we're going to have all of, so this is 282 would be the other addition pair, right, to give us 289. And then I'm going to go all the way up to pretty much where it gets cut in half. What's 289 divided by 2? About 144? So we need to start at 7 and go all the way up to 144, and that should hopefully make sure that A, B, C, and D are in ascending order. I think that's the game plan here. So how many, I guess the question is going to become, okay, once we just to figure this out, how many pairs are actually inside of here? So how many? So if we take 2 and 5, that means we start C at 6, so 6 and 283, and we go up to 144, 145, and then our last possible pairing, we can start this one at 5 and go up to 144. And so we just have to count how many pairs we would have here, right? Yeah, 144 minus 7, that seems reasonable. So there should be 137 here. And then they just go up by 1, right? 138 and then 139. $414. I don't know. Let's roll with that. I think that's not a bad go at it. Let's see if 414 is the solution they're looking for. Okay, so what do? They factor. Okay, we need to multiply the 2023. We need to add the 296. That makes sense. They find all of the divisors, which we did. Seven and 2, 89. Yeah, cool. So since blah, 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 blah. They're going to take A plus B to be 7. The three possible pairs are 1, 6, 2, 5, 3, and 4, which is what we have. Sweet, so they go from 7 all the way up to 144, 6 up to 144, 5 up to 144, sweet. And so I think we got it, right? 417, what? What did we miss? What did we miss? Okay. It's 138, 139, and 140. Plus 1. What's the plus 1? Why is it 144 minus 7 plus 1? We're including the 7, I guess, rather than taking it away. So it's really 144 minus 6. 144 minus 6, so it should be... We're just missing that extra 3, right? So this one should be 138, 139, and 140 for 417. Sweet. Cool. Inclusive, yeah, I know. Inclusive, damn it. Damn discrete numbers, always fucking everything over. Okay, no, that's pretty cool. That's a good question. I like that question a lot. Oops, I don't want to look at the solution. I haven't actually done 8. We attempted 8B and got pretty close, but we never actually attempted 8A. What kind of geometric treat are they assigning to me this year? Oh, gosh. Why do they always assign me the geometry questions? All the time. Okay, suppose the triangle ABC is right-angled at B. A, B, and C. And AB... AB is equal to n plus 1, and AC is equal to n plus 1, n plus 4. Is the hypotenuse is always the biggest side, right? Is that how this works? So AC, I guess, is, yeah, it's set up to be the hypotenuse, I think. Okay, so we know some information about the sides. And n has to be a positive integer, so n is at least 1. Determine the number of positive integers less than 100,000, for which the length of BC is also an integer. How cool is that? How well do you know your Pythagorean triples is basically what they're asking us. But we should be able to, I wonder if we can just like algebraically have a go at it and see what happens. Because my instinct says, well, why don't we just go n plus 1 squared, n plus 4 squared is equal to bc squared. My province squared plus n squared, n plus 1 squared. I think we can probably just start like this and maybe just kind of see where it algebraically goes. Right, we can expand everything out. We're going to get n to the powers of 4 here, but it's not going to be crazy algebra. And we should actually be able to factor this anyway, shouldn't we? So So if we do that and we factor out the n plus 1 squared, what's left over?
Time for a pop quiz.
So we just really need that difference of squares to factor nicely, right? We just need this difference of squares to factor into a perfect square. Should we just factor that? Then we'd have like n plus 4 minus n. Yeah, why don't we try to factor this and see what those conjugate pairs are. So if we do factor this, what do we get? We should get n plus 4 minus n, and then we should get n plus 4 plus n. Is that right? Is that how that works? That's how it works, right? Difference of squares is conjugate pairs. And that gives us some fun information. For example, the second factor, n minus n, the second factor comes out to be 4, which is great because that's just 2 squared. So it's really just this factor, 2n plus 4. So all we need is we need 2n plus 4 to be a perfect square. So I guess we just cycle through all of the possible n's. And so how does it work? It's going to be 4 less than... we're going to need to know a fair amount of perfect squares, which I'm not sure I know my perfect squares up to 100,000. So is there an easier way to do this? It has to be an even number. So it has to be an even perfect square. Yeah, we could definitely solve for n as well. Do you think that's helpful? But yeah, that does tell us some information about the perfect squares we're looking for. So I can only really consider even numbers, right? And I'm looking for the squares of those even numbers. And what else do we know? We know that... I'm just wondering if there's an easy way to be able to find these numbers. Well, let's start looking, I guess. So if these are values for n, we are looking for 2n plus 4. Oh, wait. N plus 1. We can, I wonder if we can step back for a second. 2n plus 4 has to be a perfect square number. There's a factor of 2 in here, which means n plus 1 has to be even. N plus 1 has to be even, which means all of our n's are going to be odd. Does that mean our n's have to be odd? Like none of these would work, right? If I go 2n we never get a square number, is basically what this is saying. Is that true? So 2n plus 4. 12 plus 4. 12 plus 4. Oh, this is 2. Okay, I'm dumb. This is 2n plus 2. 2n plus 2. Edder, hello, man. How are you doing? I have been assigned my marking duties for the Euclid math contest. So I've been assigned this particular question. So Loims and I are having a peek at how to solve this particular question if you want to give a go at it. We are pretty confident about the form of n. We're just trying to find all of the n's less than 100,000 that satisfy the kind of closed form that we have. Yeah, it's geometry turned algebra. Yeah, geometry turned algebra. How many hand-ins do we get to mark usually? So I usually usually have about 3 days worth of marking. That's usually what I sign up for. So I think I've signed up for like 10 to 12 hours-ish. It'll be a little different this year, but I mean, last year I probably marked at least several hundred papers. But I mean, they probably get thousands of papers. And a lot of them this year are going to be marked face-to-face, like actually in Waterloo. So I don't know exactly how many are... I think they all get scanned and they all get put online. But certain batches kind of get sent out to the people who mark online. It's really cool. It's a really cool system. So I basically just log in from my laptop here, and they give me kind of like certain batches. So there'll be like a batch of 100 to mark or whatever, and I mark all of the question 8s on those, and I'll go to my next batch, and if 8's already done, then I mark question 7. So they have a really, really nice system for marking. So yeah, okay, so I've updated this because I had an error here. So 2n plus 4, that factors to 2 times n plus 2, Brian, not 2 times n plus 1. So n is going to be even. It has to be even because it has to have a factor of 2 in it. So not only does n plus 2 have to be even, but how does it work? So n plus 2, this n plus 2 would be 8. And 8 has 2 times 2 times 2. So it has that other perfect square factor hidden inside of it. So even input, yes. So I think our n's have to be even. Yeah, our n's have to be even, which means our perfect squares that come out, all of the k-squareds are going to end up being even as well. Because if you start with an even number and you square it, the output has to be even. Yeah, so I agree with you. The input n's, I think, have to be even. And why did we say that? So we said that because n plus 2 has to be even. Right, so n plus 2 has to be even, which implies that n has to be even as well. If I take a number and I add 2 to it, that starting number is probably even. So not only does n have to be even, we also have to make sure that when we take away 2 from it, how does this work? When we take away 2 from it, nope, that's not right. So what can I say about 6? Not really much, can I? Like, how did we know that 6 worked? We know that 6 worked because when we added 2 to it, we got 8, which gave us all of the things that we needed. So we're going to hunt. How does this work? We're going to hunt for things that look like we need n plus 2 to look like 2 times x, right? N plus 2 is half of... n plus 2 is half of a square. It could be more than... It depends what you mean by half. But if we look at this first example, which is n equals 6, so what do we have? We have 2n plus 4 is equal to 16. So we know that 2n plus 2 is 4 squared. And our n was 6, right? Oh, I see what you mean. So n plus 2 has to be half of... n plus 2 has to be half of, in a division way, has to be half of a perfect square. N plus 2. So 8 would have to be half of the perfect square. Okay, that might be easier to... Yeah, that might be easier to hunt for. Would that be easier to hunt for? I don't know. I don't know. So n plus 2... to be half of a perfect square. So we could just go find all of our perfect squares. There's a lot of perfect squares though. Maybe we should find the next number that works. And see if there's a pattern, right? So if I were to continue this, we'd have 14, 16, 18, 20, 22, 24. 26, 28. Let's go up to 32. Because yeah, there might be something interesting here with the multiples of 2. Maybe it's only the kind of powers of 2 or something that are going to work. So everything down here, it's always just twice as big. So this one should just be 32, right? 32. We're really just going up by 4. So we're just doubling it and adding 4. Uh, 52, 56, 60? And then we get the next one here, when n is equal to 30. So it looks like we're capturing, this one for example is 4 squared. This one is 6 squared. This one is 8 squared. So do we always capture every even squared number? Is every even squared number divisible by 4? There's something weird in number theory about this, right? Is it every even perfect square is divisible by 4? Is that true? like the next one would be 100, right? 100 is definitely divisible by 4. The next one would be 144. That's divisible by 4 because 100 is divisible by 4. 12, 14. Yeah, I guess they're all divisible by 4 because all of the sub-factors have a power of 2 in it. So all of our perfect squares are going to land in the 2n plus 4, as long as it's an even perfect square. Yeah, Ed, yeah, perfect. Okay, that's kind of what my thought process was too. Yeah, every even perfect square has a 2 from one factor, 2 from the other factor. Yeah, so it has to be divisible by 4. So they're all going to land in this list. We just need to figure out how high we can go, right? So our only restriction is n has to be less than 100,000. So if, I guess all we really have to do is pick a big enough perfect square. I can sub it in here, right? And we can check to see what the restriction on n is, right? We can actually solve for n. So let's pick a really hefty perfect square. Let's take like 99,998. Can we go that big? If this is n, what's the biggest perfect square number that we can make? Is that reasonable or is that too big? Reasonable or too big? Yeah, this would be our k squared. So if k squared was this, the monstrosity. So if this was k squared, could we find 2n plus 4? What's n equal to here? I'm just trying to find an upper bound for what we have to check. I think this is going to be too big, right? Because if we subtract 4, we need to divide this by 2, and n's going to be way too big. So we need our perfect square number. Probably to be closer to the square root. What about 316? So this is the square root. The square root of 100,000 is about 316. So if I square 316, I get 99856. If I were to put that in here, 99856, what is n equal to? So that's still valid, and still, we're only about halfway there. So we need to find perfect squares, I guess, that are a bit closer to 200,000? Loims, yeah, I got you. So using it, ever we get... Yeah, we just need to find kind of an upper bound for these numbers. Like if I take, I need to make n about twice as big as this. So what if we went to like, I don't know, just like 600 or something? So 600 is a bit too big because I get 179,000. So we just need to kind of find the sweet spot of where we need to be able to go. What about 500 squared? That's too big. So 400 works. So 400 squared is 160,000. 160,000. And if we put that in here, oh wait, what? Is that too big? Oh no, I did it wrong. I did it wrong. 400 squared, we need to subtract 4 first, then divide by 2, and that's going to give us about 79,000. Getting closer. 450 squared, yeah, it's a little bit too big, so you think 446. Okay, let's try 446 squared. We get 198. 916. So if we put that in, what do we get for n? 198, 916. So 198, we're going to subtract 4, and then divide by 2. So we get 99,456. So this one's valid. We should probably check 448 as well. And just make sure it's, I assume it's going to be too big. So 448 squared, yeah, if we subtract 4 from that and we divide by 2, it's a little bit over, so too big. Okay, so that means we should be able to capture every single perfect square starting at 4 squared, every even perfect square, all the way up to 446 squared. So 4 squared all the way up to 446 squared. How many is that? Let's use our subtraction property and make sure it's inclusive. Is that 446 minus 3? But we have to divide that by 2, don't we? So we need all of the even numbers. We need all of the even numbers up to here, which would be 223 evens, right? And what do we have to get rid of? We have to get rid of 2 squared, right? And does this include 0 squared? I don't think so, right? So I think you're right. We're going to take our 223, subtract 1, we have 222 possible ends. Let's see if that works. Let's see if that is the logic they're using for this question. That's kind of exciting. That's a cool question too. A little bit of work there, though, isn't there? So they kind of did what we did. They did the subtraction, they factored, they got 4, n plus 1 squared, 2n plus 4. So the length of BC is an integer exactly when this is a perfect square. So BC is an integer exactly when 2n plus 4 is a perfect square, which is what we got. We note that 2n plus 4 is bigger than or equal to 6. Sure. I mean, I think that's true, right? Yeah, our smallest is 8. I guess if you take n is equal to 1, you get 7, but we've already gotten rid of that. So the smallest perfect square in this range is our 4 squared, right, which is what we have, and the largest possible perfect square is 446, given to us by Loimes, so we're going to divide by 2, subtract 1, boom, 222 positive integers. Yeah, nice. Nicely done, nicely done. That's a good question. These are good questions. I'm really excited to mark these. Okie dokie. Okie dokie. One more question for the day. Then I have to go do some errands, unfortunately. This is Euclid 2023. We're going to do 8. 8B. And Levi and I started this one. And I think we got a good part of the way through this one, but then we had a fault in our logic somewhere, and I think it has something to do with, we have to be careful because we're working with real numbers instead of integer numbers. I think that was our error. So we want to find all real values of x satisfying the following equation. So this, just some nasty square root action here, equal to 4. I think it was a little unorthodox what we did, but we kind of, I think what we did was we broke up the log base 2 4x and the log base 2 x over 64, because 4 is 2 squared and 64 is what, 2 to the 6. So I think we tried to break them up a little bit. If I remember correctly. So let's see if I can remember what we did. My first instinct is to write log x equals to y. Yeah. So we can probably do something like this. I'm thinking maybe if we start with our log 2x and we convert this one into, this will be log 2 of 4 plus log 2 of x. So here's our first square root. And here if we go log 2x, and let's go log 2x minus log 264. And then we should be able to replace all of these with Eder's suggestion. We can maybe replace all of these with y's, because everything else is going to come out to be numbers, right? So let's see what we get after doing that. So we'd have something like y times log, this is going to be 2, right? So we get 2 plus y plus 1. So this is what our first square root would look like. Second square root would be y minus 6 is what we said, right? And then there's a plus 9. So that, I mean, that looks a little bit nicer to look at. Should we just start squaring some stuff? Y squared minus 6y plus 9. Yeah, do those, oh, if those factor, that would be nice. That would be nice. So this is 2y plus y squared plus 1. And this one is y squared minus 6y plus 9. Are those perfect squares? That would make it so much nicer. Y minus 3, yeah, y minus 3 squared. Is this one y plus 1 squared? Stop it. It's not that easy, is it? Really? Wow, okay. What are the odds of that? Oh my gosh.
Time for a pop
I
quiz.
wouldn't even have noticed unless you said something, Loins. Perfect squares music. Yeah, we got this. Okay, so y plus 1 plus y minus 3 is equal to 4. Okay. So what does this mean? This means that 2y's minus 2 is equal to 4. We can divide by 2, I suppose. So we know that y must be equal to 3. But we said that y was log base 2. Oh, you are right. Yeah. So does that actually give us a couple different possibilities to look at when we try to remove these square roots? Yeah, okay, I gotcha. That is right, so there should be absolutes here and here, right? We need to make sure these are going to be logarithms, so we should be able to get through some of the cases a little bit easier. But there's 4 different cases, right? Okay, so if we do the number line business, and we look at -1, and we look at 3. Can we include, and this is for y, right? This is for y. So it's going to change a little bit when we go back to x. So I'm trying to remember how to do this again. It's how does this work? We have to pick values kind of inside, right? Inside the intervals. So like for example, we could test out y is equal to 0 and see what happens. I mean, this seems to be okay. If y is equal to 0, we're going to get 1 plus -3. This seems to be okay. Yeah, 4 equals 4. What if we test a value up here? What if we take something like y is equal to 4? We would get 5 plus 1. So it does not work up here. And then finally we could look at a value down here. We could take something like y is equal to -2. Less than -1 doesn't seem good either. Okay, so if we take -2, yeah, that's going to give us 1, 5. Yeah, we're going to get their mirror image, right? So it looks like, and we can include the endpoints, I think, as well, right? So we know that this is good. Can we include -1? -1 would give this as 0. This is 0. And -1 would give this as +4. So yeah, we can include -1. What about 3? I think 3 would work as well. So we have a range of possible y values. And if that's the case, we could see what happens to these endpoints, right? And make up a new interval for the log base 2 part, right? For an interval for x, essentially. So if we want the lower bound to be -1, I don't think we can make that work, right? No, we can make that work. And if we want the upper bound to be 3, we should be able to make this work too, right? So what value would work to make 3? That's going to be x is equal to 8, and we need x is equal to, yeah, 1/2 here, right? And anything in between anything in between 1/2 up to 8 should be permitted, which is kind of crazy. I think that was the bit that we were missing. We were missing, I think our error might have been we forgot to apply the absolute value bars here, right? And when you do that and you look at the number line, it's a bit clearer that you're gonna get a range for y, which means we should get a range for x. So I think that must have been our error the other day. Let's take a quick look at the solution key. And let's look and see if we have the right kind of logic here. So what are they doing? Okay, so they're applying the kind of perfect square stuff that we did. They're looking at the possible cases. So when log 2x is... What? When log... Therefore, f of x equals 4 exactly on the interval from -1 to +3, which is what we found, which is true when x is between 1/2 and 8. Nice. Okay, so we were able to solve that one. Very, very cool. I know, and it's so funny because it's a mistake that I always show my students when I'm teaching calculus, and I fall into the same trap. I fall into the same trap every once in a while. Every other day I get a post from someone who doesn't realize that the square root function only returns your positive square root. Yep, and not the negative. Yep. It's the problem. It's the problem with those parabolas, right? They're not one-to-one. And look at that. I have finished my rosé for the afternoon. We've finished marking a couple, well, we've finished getting an idea for how to mark these questions next week. So I think with that said, I didn't get anything, I have a couple things happening in here. Oh, just some stuff from Andy, but I don't think that's relative to the stream today. So I think with that said, yeah, Eder, thanks very much for popping in and helping me fix up my solution key for this answer here. So much appreciated. Loims, thanks for the emotional support as usual. And I'll be back tomorrow. So tomorrow at 3 o'clock. So if you guys do have some mathematics questions you want to take a look at as you start preparing for your exams, tomorrow afternoon, 3 Pacific Standard Time, I believe. We're not on daylight savings time anymore. So until then, hope you guys have a fantastic rest of your day. And stay positive. We'll talk to you soon.